Morning guys, and welcome to another fantastic and amazing tutorial for simulation. Now, as I said from the start, I'm intending to try and show you the benefits of not just sim multibody, but I also want to show you other options. I know Solidworks gets a bad rap as far as simulation goes, but what I want to do is I want to use Solidworks as well, so you can make your own mind up. I do need to tell you, Solidworks is limited at certain aspects. There's some things that Solidworks will struggle, if not find totally impossible to do. However, when it comes to basic closed systems that are all connected, it actually does a pretty good job. What we're going to do is we're going to do a second order system. Now, so far we've done it in Simulink, we've done it in Simscape, we've not quite done it in Sim Multibody yet. But I thought doing it this way would be a nice way to try and connect into Sim Multibody. So first things first, I've opened up SolidWorks. What we're going to do is a basic mass. Now what I need you to do is follow me through this process. So I'm going to go new and we're going to go part. Now coming from the top plane, again the top plane, I'm going to go to sketch and then sketch. So I'm in my sketch, I'm active, ready to go. Now from the corner rectangle, drop down the arrow. You see where we have a center rectangle? We're going to come from the center because I want this to be my midpoint of everything. So what a lot of people are not clear about is SolidWorks actually ties in to its original of where everything goes. So I'll show you what I mean as we're going through. So I'm going to left click and draw a corner rectangle, well, center rectangle I should say. From there I'm going to go smart dimension, and what we'll do is we'll do a profile 10 by 10. So I'm going to smart dimension, let's put in 10 millimeters. Again, still on smart dimension, left click on the bottom, and I'm going to change that to 10. Then, now you must follow this. If this is done wrong, this will not work and you will be incredibly peeved. So what I'm going to do is go features, extrude boss base, see how the arrow travels upwards. What we're going to do is we're going to assume that the top end of the actual mass is going to be the fixing point for our spring and the damper. So you see on the direction over here where my cursor is, if I left click, change the direction, and I'm going to click OK. Zoom to fit. And what we've got now is our mass, basic mass. So then, come back up to the top, go to save as, and you'll notice that I've been messing around with this already, but I'm going to overwrite that. So I'm going to call this mass, click save. And mine's only asking to replace the present part because I've been playing around with this morning. So click save. Right, so that's all we got. We've got a brick, but the beauty is our origin. You see where the origin sits? Origin sits bang at the top. We're going to use as much as this as possible to our advantage as we're going through. So that is now done. Amazing, right? So what I'll do is go to new. What we need to do now is we need to tell the system that this mass is going to be something that's used as an assembled point. So I'm going to go to assembly and I'm going to go OK. Obviously, because the mass is open, the mass is introduced. Do not just click anywhere. What I'm going to do is I'm going to say to the system, when I click in, I want the system to decide based on the original geometry that we did, because you remember we did an extrusion downwards, so that means that the origin to this piece will be in the middle at the top plate. So in other words, don't click anywhere, just click the green tick, and then you see there it moved, right? So if I go origin, you'll see it's actually on there already. So what it means is that it's used the origin from the assembly, used the origin from the part, and it's actually connected the two together. If I just click anywhere, these origins will be separated. So it's one thing to keep in mind for if you're doing anything in the future. Right, before we progress, let's click save. We need to save this and we'll call this mass spring damper. At the end of this, by the way, I'm going to leave you with a challenge, which should be very interesting. So, we've now got his mass. We've now got the assembly in position. Now, I'm going to just point this out. A lot of students I've seen do this. So let's go down. I'm going to go to motion study, and then I've had students say to me, "I've done the motion analysis. See ya." This is totally and 100% wrong. Totally wrong. First things first, let's get back and let's set up the simulation first. Now, I like to always be in control of where things start from. I don't know what you're like. I like to be able to say, I'm going to start this at 20 mil. I'm going to start this at 50 mil. Who cares? I don't give a shit. What I'm talking about is I want to be able to control the distances. So, because we've been specific about how this thing's modeled, if I go to top plane, see there, you go, well, where is it? Zoom out. You go, oh, no. So if I bring my cursor over the top plane, you'll notice these key markers. Now this is just like in any sort of Microsoft software. I'm going to drag it and just manipulate it. The second you manipulate it, it realizes you're trying to bring it into the normal size of the geometry. And nobody wants to piss around for the next 20 minutes trying to get this right. You see where my cursor is? Still on the actual marker. Right click. You go to features of top bit. There. Auto save. Click auto save. Oh, auto size. Ah! That didn't work out so well. Give it a minute. And this is what annoys me. This is another thing that annoys me with SolidWorks. Use your zoom. Roll it backwards and forwards, and what you'll find is that all of a sudden it's the same size as your actual target. Now this would imply that the spring and the damper would be completely flat and it would not work. You know, it'd become totally flat, so it's not a realistic representation of what we're talking about. So what we need is, right, sorry about that, I got interrupted. So as I was saying, on the top plane now, it sits completely flush with the actual mass itself. It's not a true representation of a spring and a damper. What we need is a starting position. So with the top plane selected, I'm just going to reselect it so you're aware. I'm going to go to reference geometry and plane. So you notice this offset. It's offset of 10 mil. You can set the 10 mil whatever you want. This is the start position of where we're sitting. So what I will do is click OK. This then confirms what my starting point will be. So in fact, you see where I have this plane, I'm going to left click once. I'll show you this again. So if I left click, then left click once again, that's a shortcut to renaming. So I'll call this starting point. Right, now to assist in the thing of actually seeing everything, you see how you got this eye. This eye is brand new, by the way. So if I drop the arrow, what I'm going to do is click on view planes. This then allows me to see where my starting point will be. Now, avoiding that error that I was talking about earlier, by the way, save. Avoiding the error that I was talking about earlier. You see where we have the gear here? To the right side we have options. To the right side we have an arrow. So I'm going to drop it. On the arrow you'll see add-ins. SolidWorks, like ANSYS, like anything that's right. Oh, sorry, I keep getting interrupted every 2 minutes. So let me just catch up with where I was. So from the gear, we'll go to the right arrow. I'm going to drop it down. On the add-ins, I'm going to click onto it. Now, like ANSYS, like everything else, SolidWorks will shut off anything that's not needed, and it tries to minimize the amount of things that you need. Now, what we're going to do is we're going to scroll down, keep coming down. You notice how I've got SolidWorks motion. You can either have it on startup. Warning, if you put it on startup, it will slow down your PC. Not drastically, but it's just something to keep in mind. I like to manually add these in, so then it turns itself off automatically, keeps it slick, and then if I need it, I add it in. So yours won't be checked. Make sure this is checked, then click OK. Now once you've done that, what you'll get is absolutely nothing. Nothing's happened yet. So from this position, I'm now going to go to the bottom, now go to motion study, and yes, it's still the same as before, but there's one interesting element that I've now added. See, we've got animation, which just is basically this thing moving. Interestingly, with the animation you can make rendered videos of explosions, things like that. Exploded views, I should say, before anybody gets the wrong idea. So if I drop that and then go to motion analysis, now this is different. Now we're on actually in the no frills version of MSC's solvers, the Adams solvers. This is a very respected solver, but it's not as respected as things like MATLAB and things like that. I mean, MATLAB does use the Adams solver, but it's only one of its 45 different solvers that it can use. Anyway, let's get to it. Right, first things first. What's one thing that we know for sure that this system's going to be affected by? Gravity. We know gravity is going to act on it. Now, keeping in mind of the datum itself, what we're going to do is put gravity in Y so it acts downwards. From the list here, we have videos, we have motors, we have springs, dampers, force, contact. We will actually hit contact as we're going through, by the way. And we've also got gravity. So I'm going to left click on gravity. You notice here on the bottom right, it automatically says everything's in Z. Very similar to MATLAB, interestingly. Very similar to MATLAB. But like I said, we're going to put this in Y. We want this to act like gravity. So I've clicked onto Y. You'll notice here, it's gone down. Also, you'll notice I can play around with gravity. So I can look in space conditions, I can look being on Mars, or I can look at other elements if gravity has changed in any form or any way. So I'm going to click on the green tick, and that is now gravity added. See here, it runs over 5 seconds. This is a default time speed, and what we're going to do is we're probably going to trim that down. But for the minute, we'll leave it at 5 seconds. So this is as mass in position with gravity being affected. Also on the starting position, we've now got a point where this is going to sit. So if I zoom this out, you'll see the plane here. Now that will be my point where my spring and my damper are both fixed to my mass that's beneath. Right, so we got gravity, and if I go to spring, so I'm going to go on to spring. From here, I can, there's a few ways of doing this. But because we've been very sophisticated and we've decided to use a starting point from a plane that we've decided its distance, it allows us to automatically define the spring's free length. So I'm going to left click onto it. You see here it's identified itself as a starting point. Now you remember at the start when we automatically made the plane suit the same size as the mass. This is where it makes life so much easier for us. Click onto the top plane. Now don't get me wrong, you look at that, this is just a hyper rendered version of how the spring would look. You notice it's heavily in compression. We are going to change this, but you can see that it's heavily compressed. Right, so you notice if I spin it round, it's now sitting from the central point. So I've chosen the face, I've chosen the top. Now an interesting thing with the top plane, if you do not get this the same size as the mass, because it's coming from the center of the plane, what you end up with is a spring that's hanging to the left, hanging to the right, and it's not exactly to the configuration that we want it to be. So now this is only a very small mass, so I'm going to set my K value to something very small. So I'll go 0.01 millimeters, sorry. Just to introduce you a bit further into this though, it's again, Solidworks gets such a bad rap about being this awful software. It's not true at all. So if we go down the list, look at this. Now a lot will look at that and go, why is the damping in a spring? This is natural damping of the material. If you know what the natural damping of that material is, its ability to damp naturally, you can actually add that in. For this, we're going to stay on the similar sort of system that we've done when we've done the script version, when we've done the Simulink version, and when we've done the Simscape version. Again, I'm doing this because I want you to make your own mind up about this software rather than just listening to, I don't know, opinions that 90% of the time are not correct. Right. So what I'm going to do, again, this monstrous spring is not a true representation. What we're talking about here is this is the key. Our spring stiffness, that is what we're talking about here. So let's click OK. Oh, before we go down, go to display. Say we got this here. If I change this, this is just display, so this is what I can see. So if I change that to 1.5. See here how it slims down? That's because I've changed the diameter of the wire itself. I can do the coil diameter, so let's drop the coil diameter, let's go 8mm. You see there, it starts to look a bit more like you'd imagine a spring loaded in this kind of condition to look like. Again, this is just a display, this is not anything that's going to give us something useful, if you will. This is just for us to see something. So, once we got that, I'm going to scroll back up to the top. Oh, another thing, torsional springs. Sometimes you will need to apply torsional springs. They're a very useful thing for use. For this, I'm staying with linear springs just because we're looking at the mass spring damper example. So I'll click OK. Right, so that's us in. We're still on 5 seconds. It's a long time for this. But what we'll do is we'll get this thing set up, we'll get it running, and then we're going to see how this works. So next to the spring, we have damper. Linear damper, you can have a torsion. The torsional damper, by the way, is something very new. It wasn't always there. It's a new thing, very useful though. So start with we'll stay with linear. So I'm going to go from my start point onto the top of the mass. Now this is one thing that always frustrated me. No picture of the damper. When we used to study MSc Nastrom, it used to give us a picture of the damper. It made life so much easier. I say that, but it's not that difficult to get used to. So let's stick in a C value. Now, as we know so far from some of the stuff that we've done, the damping will always be at a factor outside of the spring stiffness. Now we're going to put it outside of a factor of about 100. So with that in mind, if you remember, for the K value we went 0.01. So what we'll do with this is we'll go 0.0, let me think, 0.0001. So it's a factor of 100 out from the K value. If I click OK, now you see here we've got these orange lines. These orange lines are key markers. I don't know what you could do if you wish, but you can turn gravity off at a certain time if you wish. So let's say you get to a point and go, no, I want to presume that gravity is no longer active, and you can shut it off. But to keep this as simple as possible, to aid in the process of what we're doing, we're going to leave it on for the minute. We will come back to this, by the way. So if you've not done it already, make sure you hit save. First thing we need to do is make sure this thing runs. So from where you see motion analysis, to the right side you have calculate. So click calculate. And you go, what? I do understand. I'm just being facetious. This calculate is trying to calculate what's going on. Agreed? Right. So it means something went wrong when I first brought the mass in. This is one thing that it's caught me out for years. It catches loads of us out. When Solidworks first brings in a component, it assumes it's fixed to the ground. It likes to give you a reference point to start to build from. So, because if you didn't, it would mean that when you go to build an assembly, every time you grab it, it might slip, and it can lead to a lot more frustrations. But because this is the only component that we're going to use, what we're going to do, you see on the design tree, we've got the mass. Right click on the mass. If you go down the list, you'll come to float. It's because when it was brought in, it was set to fixed. So click float. And then let's try it again. Oh, You notice there was slight motion. This is where we need to tidy things up. So first things first, we need to look at the output, because the aggression of that type of response is not something that looks very good. So first things first, here you'll see results and plots. Left click results and plots. From the results, drop the category and then go to displacement, velocity, acceleration. First, all I want to see at the minute is I just want to make sure that the displacement of this is something realistic, that there's no errors, that it doesn't look quite poor, if you will, as far as an output. So then go drop down again, and we have linear displacement, and we can choose magnitude, which is essentially everything taken into consideration, or we can choose just Y. Now, from what we've done in Simscape and Simulink and on a script, we were looking specifically at the Y component. So just for completion, I'll stay with the Y component. And then you'll see here, it literally says, do you want to choose a specific point to look at? Now I think with this, what I'll do is I'll just choose a top face. You don't have to, by the way, but I'm just going to choose a top face. I can track its position. And you look there. Now, the way that this system is responding, we know instantly the way that this system is responding. It responds within 0.5 of a second. So, let's bring this over. And then let's drag the time bar back. So it means really all we need to run this for is 1 or 0.5 of a second. I think we just go with 1 second. Still gives us that freedom for a little bit of configuration and changes. So you see at the top you have a black key properties bar. This is set to a default of 5 seconds every single time. But if I left click, keep my finger on it and then drag it, go back to 1 second. Now this is something a lot of people have missed. I missed this for years. Over, go down to the right, you have zoom, zoom in, zoom out, or you have zoom to fit on the time bar. So click on it. This now expands to show us the full time that we're running at. So let's run it again. Ooh, it's not good. Look at this. This is an iterative process which is in essence showing that each time segment, each time section, think of the first the first script that we did where we were choosing a time step, we were choosing that iteration. Solidworks is doing the exact same thing. These are the Adams solvers, by the way, and when we were using Simscape we used the Adams solvers. So this would instantly tell us the time step is too small. So let's jump down. See how we have properties? Well, we have the gears. These are options. So let's click on options. This is options within the motion analysis. You can use precise. The issue is with using precise, this is your equivalent of variable time step that we get in MATLAB. You can use that if you wish. It does slow down the system, heavily slows down the system. This is very interesting. This is frames per second. Now with frames per second, what it tries to do is it tries to slow down the process of calculation. It tries to essentially try to stay with this time step, but it doesn't edit the time step. It gives more time for computational processing. So what we're going to do first is we're going to in fact we're going to I think we're going to times that out by 10. So we've got 250 frames per second. This might not heal it, but let's just try it. So I've clicked OK and let's recalculate. See how this nice smooth motion's occurring? Now you look at that. Questionable. You see some of these oscillations here. Now I can't really zoom into that area, but you see this point here where it almost turns into a line. Some could argue that that is actually an error, where the iterations weren't sure where it was going to be, similar to when we had a huge time step on the first order system. So what we could do is go back to the time, back onto here, and you see when we have the accuracy, just notch it up by 1. So we've got 0.0001 segment per second. I don't think it is, but it's just healthy to see these processes so you're aware of how to do it. Recalculate. Now look at that. Still remains, but you're starting to see a smoothness that's occurred within it. I don't think that that's really error. We could put more time steps on that. We could put more frames per second on that, but it's very smooth output. And even looking at that, look at this. You still have some behavior beyond 1 second. So what I'm going to do is just boost it up and go 1.4 seconds, and let's run it again. Let it reach that steady state. Yeah, you see here we have the steady state that's emerged here. So we know that the mass started and it reached steady state at, there's an estimate of 1.2 seconds. Right, so that is our displacement. Let's just take a look at our velocity, because you remember on the Simscape model that we built, we did pull out velocity and also acceleration. So I'll do velocity, and I'll leave you to do acceleration. So I've picked velocity, and I'm going to go in the Y component, and I'm going to choose the top plane again. Again, if you're starting to measure the same place for different things, make sure you stay with the same position. Sometimes it can affect your outputs. Not all the times, but some. It's just so it's healthy to always stay with the same selection. Click OK, and there we go. So let's bring that down. Now I should point out in the notes that you have, which are simulating second order systems, you have the exact and you have Euler's methodologies for calculating it. We've done some of that. All verification you can pull from that. When you tie these in together, when you run these through MATLAB, through Excel, any of these really powerful tools, it allows you to do that, and you'll be able to get a nice plot which will map this almost identical. I emphasize on almost because there's always going to be hit and miss issues. Right, so yeah, you've got your plots here. Come over to your results. Now let's say, for argument's sake, I'm thinking, right, what I need to do is I want to be able to get this out, I want to be able to do my manual calculation, and I want to be able to put it into Excel, and then I want to do my manual calculation for verification of the results I'm getting. So let's go with linear displacement. If I right click, this is on the linear displacement. Scroll up, export to spreadsheet. Let's go export to spreadsheet. Any minute now. This can take its time, clearly. Right, there you go. So this is the export. So let's just check on the graph. Let's go data, chart tool, sorry. Right, so get onto chart tool, and I am just going to look at chart type. No, that's an axis, sorry. Format. It's always oh, chart type, there it is. Sorry, I'm being blind. So I've just clicked off, I've gone for my smooth scatter plot. It's a bit easier to see, and I'll just change that back to white. So you see there, that's the overall output that we're getting. To pull all your data that it's plotted to sheet 1, this is all your data that it's plotted. One thing to always keep in mind if you are going to do verification is make sure you look at the time step, make sure your time step will match against it, or make sure these things are considered, or else you'll end up plotting something and it will be a factor of 100, 1,000 or whatever out of what you want to do. It is a very useful tool, really useful tool. So if you've not done already, make sure you save this, because now we're starting to explore the idea of across multiple softwares, across multiple elements, and just showing that Solidworks, like I said, does get a bum rap as far as the simulation tool goes, but as you should be now starting to see, we've just reproduced what is done through theory, what we did on scripting, and also what we did on Simulink. When we move on and we go on to the piston assemblies and things like that, I intend to show you from both sides as well, just because I want you to be aware of that this is not a software that you just write off. I hope you found this useful, and if you have any questions, please feel free to email me or come by the office and I can try and help you along with this even further. Speak to you all soon.